Okay.
We just have the quantitative one class, and it's talking about the correlation. So there is the explanation about the correlation. It cannot address the non-linear relationship. The relationship cannot be understand.
This one I explained it yesterday. So if the relation is not linear, if this kind of relation, then it cannot detect.
Okay.
And then categorical variable. So if it's not number, you cannot use correlation.
Yes.
Exception is binary. 0, 1, 0, 1. Then you can do tetrachoric correlation. That is only exception. We have good support from good. Okay. I thought. Okay, so Hmm. No? Hmm. 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 Okay, everyone. Online students,
Yes. Yes, Professor.
hear my voice?
Yes.
Okay, that's good. Okay, good afternoon.
Yes, doctor.
Okay. Did you see the video of yesterday's class? Some of you missed the class, right? Okay. Okay, so yesterday we finished this discussion. We talked about the error term, epsilon. Okay, so the actual data and the estimated line, straight line, are not exactly the same. Okay, there's always some deviation from the line. So that's how actual data are. Okay, and that deviation is captured by the epsilon, this term. Okay, so let's summarize, not just summarize, introduce some terminology about the regression analysis. Okay, we start from simple regression. Okay, simple regression has a specific meaning. Simple regression means one independent variable. There's only one x variable, which is not so useful. Okay, so in your actual research, we will not use it. Okay, but just as a way of understanding the concept, we start from this one. Okay. Tom. Okay. Okay. So now we have two equations. First one is predicted value of y. So this one has no epsilon. Okay. So what does this one mean? What does this one represent? This one represents the line. Okay. Regression line. The model, not the actual data. Okay. Okay. So predicted value of y. We use this notation y hat. Y hat. Okay. It's not y, but y hat. It means the predicted value. Okay, so once you find the coefficients b, b0 and b plus, and then you specify x value, then you can predict the y value. Okay, so that is basically this straight line relationship. Okay, so that one has no error. Okay, the second one, this one includes the error term. Okay, so this one represents the actual value, actual data. Okay, so this one is not exactly on the line. Okay, so this one specifies the line. So this one specifies the actual dot. Okay, so the first one is about the line. The second one is about the dots. Okay. Yeah, as I explained yesterday, this subscript I. We often use I, but sometimes it can be K, S, P, or something else. But we often use I. Okay, so this one is the identifier of observation units. Okay, so it's like an ID number. If it's household, then it's like household ID. If it's individual, then it's like individual ID. If it's district, then it's like district ID number. Or it can be district name as well. Okay. So I refers to the ith observation unit. So if it's a sample of 100 households, then I goes from 1 to 100. Okay, and there are 100 dots. Okay. Okay, now X. X, I already said, is an independent variable. But there are other names as well, other terms. For example, explanatory variable. Because X kind of explains the Y value. Okay. Now, predictor variable. Yeah, X is a predictor of Y. Okay, so X explains Y, X predicts Y. Okay, so similar meanings, but different terminology. So sometimes we say a predictor variable, or just say predictor. Okay. So in this case, we have one predictor. Okay, another terminology, regressor. This is also sometimes used. Okay, so now we have one regressor. Covariate. Covariate, if we have only one X variable, we don't say it. But if there are more, okay, we sometimes use covariates. Covariates or covariate variables. Okay, right-hand side variables, or RHS, because it's on the right-hand side of the equation. Okay, right-hand side of the equal sign. So that is why sometimes we just say right-hand side variables. Yeah, sometimes the right-hand side variables are explanatory variables, but not independent variables. That kind of thing can happen. Okay, right-hand side variables may not be always independent. Okay, so these are not totally synonymous. But yeah, 90% of the time, you can consider them as synonymous or interchangeable. Okay. Okay, now on the left-hand side. So Y is usually, we call it dependent variable. Okay, it's dependent because it depends on X. Okay, so when X is determined, then Y is accordingly estimated. Okay, so X comes first. So that is why we refer to X as independent and Y as dependent. Okay. Response variable. Sometimes we say response variable. Okay, to mean the left-hand side. Or you can also say left-hand side. LHS. Okay. Okay, now on the right-hand side, apart from X, we have coefficients, right? B coefficients, B naught and B sub 1. Okay, so B sub 1, sorry, no, B naught, this one. this one. Okay? This one can be called y-intercept or y-intercept term. Okay? Because that is where the line cuts across the y-axis. If this is the line, okay, this value is b naught. Okay, and then this slope is b sub 1. Okay, so it's intercept because it here the line intercepts the y-axis. Okay, so y-intercept, or we just say intercept sometimes. Okay. Yeah, we also often call it constant. Constant term or just constant. Okay, so when you present a regression result in a table, in most cases, you need to show this as well. Okay, and then you use this constant. This term we often use. Oh. Yeah, so in the table, you write constant and then show the value. Okay. Okay, B1. B1 is the most important. B1 is the most important purpose of doing this analysis. Okay, so basically you want to find B1. B0, you don't care. Okay, you're not really interested in B0. But B1, it's something you're most interested in. Okay. Okay, so this one, slope coefficient. If it's a linear model like this, because it captures the slope, like this one. Okay. So if B1 is large, then the line will be steep. Okay. Oh, it will turn off. Okay. Let's do something proactive. Oh. Okay. How about this? Okay. Now I think it's okay. Okay. So B1 coefficient. Yeah, you can say slope coefficient. Or you can just say coefficient. That is also fine. Okay, now the rest is the epsilon. Epsilon, as I said, error term, but there are other names also. Stochastic term, disturbance term, or sometimes we say random error. Okay, like also white noise. Okay, there are some other terms. Okay. Now, after estimating the B coefficients, okay, after estimating the B coefficients, that means after drawing the line, okay, after deciding the line, okay, and then you can consider the difference between the actual dots and the estimated line. Okay, so after the estimation, we call this epsilon term residual. Okay, residual is like something that's not explained. Okay, so the value of y is to some extent explained by x through these coefficients. Okay, but because of error, not perfectly predicted. Okay, so that that portion of y that is not explained by x, we call it residual. Okay, so the same as error term, but the context is a bit different. After estimation, but is not yet explained. Okay, so that is the idea, okay, behind this term. Any question about this? Just terminology, so you just need to get used to it. Okay, so now, as I said yesterday, how do we determine B coefficients? Okay, we will calculate B coefficients so that the error will be minimized. Okay, that is the basic strategy. That is what this analysis does. Okay, so we minimize the error terms. That way we will find the set of coefficients B0 and B1. Okay, so now in this model there's only one x variable. So that's why you have only two coefficients, intercept and one slope. Okay, but when you add more x variables, so in the actual research you have to add more. Then there will be more coefficients. Okay, there will be more than one slope coefficient. So B2, B3, B4. You will find them at the same time, not separately, at the same time. That is the most important part. Okay. Okay, so the simplest case, okay, one independent variable case. In this case, the two coefficients B0 and B sub 1 can relatively easily be calculated like this. Remember these notations? So let's look at the slope first. Okay. Okay, what is R? Oh, sorry. We discussed it yesterday. R is actually correlation coefficient. Okay. So this can be positive or negative or 0. Okay, but the maximum is plus minus 1. Okay, so that is R, correlation coefficient. Remember this S sub y and S sub x. Still remember? This is from last week. On Wednesday. Yeah, Wednesday last week. Forgot? This S, small s, okay? Small s indicates sample standard deviation. Okay, sample standard deviation. As opposed to this one. This is the counterpart for population, not sample. Okay, population standard deviation is sigma. Most of the time we don't know it. Okay, but the sample standard deviation you can easily calculate because you have the sample data. Okay. Okay. So in your sample data, this is the standard deviation for the x variable. This one, sy, is the standard deviation for your y variable. Okay. So if it's the one independent variable model, simple model, it's not so difficult to calculate the slope. Now the intercept. Intercept coefficient equals, what is this one? Remember, we discussed it a bit. It's not y. but y bar. Sample mean. Okay. Yeah, if it's population, then mu. If it's population, mean. Okay, but you don't have population. You have sample. Okay. You don't have to worry about population now. Okay, because this y bar is the sample average, sample mean of your x variable, of your y variable. Okay. Okay. So this one fine. Minus b1 times x bar. So x bar is the sample mean for the variable x. Okay. So just calculating average, nothing difficult. But you need to have b1 here. So b1 you calculate first. Okay. Yeah. So b0 and b1 are related because we have b1 here. Okay. Yeah, but of course you don't calculate it by hand. The software will do it. Okay. So this is the case of one independent variable. Relatively easy. Okay. Now, so as I said, this is the result of, okay, so what I just shown here. This is the result of minimizing the errors. Okay. That is how we arrived at these two, these equations. Okay, so let's look into minimization of errors. Okay, so first of all, this method of finding the coefficients by minimizing the errors, we call it least squares method. Okay, so this kind of method, that is the terminology, least squares method. More specifically, when the error term is random, error term is the epsilon. Okay, sometimes error term is not random. It has some patterns. Okay, then we have to think about some other models. Okay, but if you are lucky and the error term is completely random, then this model can be called ordinary least squares. Okay, not just least squares, but we put ordinary. Okay, so this is the luckiest case. Yeah, but usually we don't spell it out. We call it OLS. Okay. So when you say linear regression, usually people are talking about this one, OLS. Okay, most of the time. Linear regression or multiple linear regression or simple linear regression, either way. It's the same meaning. OLS, linear regression, okay, least square regression. Okay, so now we consider this term, squares. Okay, earlier I said we minimize the errors. But now we are talking about squares. Why is that? Okay, let's think about taking the sum of all the errors. Okay, so there's error, there's error, there's error, 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 error. Okay? Error is the vertical distance between the actual dot and the line. Vertical distance, that is the error. So think about taking the sum of all the errors. Because we try to minimize the errors. Okay? Okay, now we also think about taking the sum of squared errors. Which one will be better? So this one may be about 5, right? So this is 5. This one, maybe the error is like -3. Okay, so this one may be maybe +3. This one may be 0. Exact. This one may be -1. Okay, so these are the error values. Okay, so when you consider the sum of errors, what will happen? You take the sum of all these numbers. Because the error is supposed to be random, these dots appear on both sides of the line. So error terms are both positive and negative, right? So if you take the sum, it will be close to 0, because the positive and negatives cancel out. Okay, so that is not a good indicator when you consider minimizing the errors. How do you define the errors? If you just take the sum, then it will be like a 0, right? So that is why we consider this one, sum of squared errors. So each error value, you take the square. Then what will happen? This will become 9, right? This will become 25. This one, this negative will become positive, right? So this one, after taking the square, it will become positive number. So all the numbers will be positive by taking the square. Okay? Then you take the sum. Okay? You add up all these numbers, 25, 9, this 9, +1, all those squared values. Okay? Then it will not approach 0 because it was already taken to squared. Okay? All the values are positive. So they don't cancel out. Okay? So that way you can measure the magnitude of errors. Okay? So if errors are, not errors, the actual dots are located very far from the lines, then error values are large, right? So that can be captured if you consider sum of squared errors. Big errors are captured as big numbers. If you don't take the square, if you do this one, just the sum of errors, then, yeah, whether the errors are big or small, either way, it will be 0. So you cannot really assess. Okay? So that is the reason why we consider squared errors. And that is why there's this terminology here. Okay, we don't say least error method, but the least square. This laser pointer doesn't work. Oh, okay. Okay, so least squares. So that is the meaning of squares. Okay? Okay, now let's have some example. Okay, one independent variable. Okay. Okay, now the dependent variable is non-agricultural income. And then one independent variable is years of schooling. So that's what we observed yesterday. We look at the correlation, we looked at the scatter plot. Okay, so now we are coming to one independent variable regression. We apply this to these two variables. Okay, so let's go to R. Okay, please open R. Yeah, like this one. Okay, after opening R, you open the script file, right? So now you're working on R script 5 to 11. So that one you open. Okay, then I just enlarge it. Okay, you go down, you finish the plot, correlation. So next to correlation, you have this one. Start of regression analysis. The first one is simple regression, meaning there's one independent variable. So in this case, years of schooling. Okay, so there are two lines. Oh, well, let's read the data. Okay, unless you already opened it. Okay, remember this one at the top. So this one you select, or you just put the cursor, and then execute. Execute means in Windows, Control R, in Mac, Command Enter. Okay, so execute, and then the File Explorer comes up. You select the CSV format data file. Okay. And then after reading, don't forget to attach. Okay, so now you execute this second line, attach data. Control R or Command Enter. Okay, so when you see no error message on the left side, it's a success. Okay, so now your data were read and attached. Okay, so going back down to simple regression section. Okay, you have two lines, right? The first line is to execute the calculation. But just calculate, it doesn't show the result. Okay. So the second line is to show the calculation done in the first line. Okay. So in the first line, I just named the result under simpreg. Okay, for simple regression. Simpreg. So this name can be anything. This is an arbitrary name. Okay, so you can give any name. Okay, so that part is not our language. On the right-hand side, starting from this kind of arrow. Okay, so that part is the language. Okay. So this one, it's not real arrow, but it mimics an arrow. Okay, so this basically means you do some calculation according to the right-hand side, and then the result is stored under this name on the left-hand side, simpreg. Okay. So in many cases, the syntax is like this. Okay, so it's convenient if you have some understanding of this language syntax. Okay, although you don't have to type anything. Okay, so on the right-hand side, this basically calculates the regression coefficients. Okay. The language is very simple. LM, linear model. Okay, LM, lowercase. Okay, so that's it. The rest is just variable name. You put the dependent variable first. Okay, and then put the tilde, this wave. And then you put this independent variable, years schooling. Okay, so that's it. Okay, now you can execute these two lines together as a set. Okay, please execute. Did you get the result?
Yes.
Same. Okay, so it shows the regression result. Since we only have one independent variable, there's only one variable shown. That is years of schooling. Okay? So next to the variable name, you have this number in the column estimate. So this estimate means coefficient. Estimated coefficient. Yeah, sometimes we simply say it's an estimate. Okay, so this is about coefficient. Okay, so the coefficient of years of schooling variable is how much? Hmm, 2,906. So that is a slope coefficient you are looking for. Okay, but don't forget, you have to check the p-value always, because it's statistical analysis. Okay, so pay attention to p-value. That is actually the first thing to look at, even before looking at the coefficient. Okay, so what is the p-value for this slope coefficient? Hmm, 0.0008 something. Is it large or small? This is very small. Okay. So when p-value is very small, then this estimated coefficient, 2,906, okay, we conclude that the coefficient is, it's real. Okay? It represents the effect of years of schooling on non-agricultural income. Okay, so there is an effect. That is the conclusion based on this coefficient and p-value. How about the intercept? Remember intercept? Intercept is the coefficient B0. Yeah, so that is presented here, just above years of schooling. Okay, so this means B0 is 12,880. Okay, now p-value, 0.035. Yeah, many researchers consider this p-value as small. Okay. But maybe some researchers in natural science, engineering, maybe they will not trust this number. Okay. But because it's a social science survey data from relatively small sample, yeah, conventionally we conclude this intercept term is significant. Okay? Significant means a p-value is small enough. Okay. So the meaning of significant is the estimated coefficient is okay. That is the meaning. That's the meaning of significance. P-value being small. Okay. That means the result being significant. That means the coefficient is different from 0. Okay. Otherwise, if p-value is large, then basically it means the coefficient is not different from 0. So we regard that coefficient as 0. No effect, no slope. Okay. That will be the implication. If p is large. Okay. Not this case. This case, p is small. So we conclude that the coefficient is not 0. We kind of believe in this number. Okay. Any question about simple regression? This is just a starter. Okay. Then we will increase variables. Otherwise, it doesn't make sense. Because of what I explained yesterday. So one variable is not enough. Okay, so now okay, so as usual, when you get the result, you present it nicely. Yeah, in a table looking like this. Okay, so you do some decoration to make it easy for readers to understand the table. Okay, so coefficient, of course, you have to present the variable names. Okay, and then, yeah, good practice is you put the unit as well. You don't just put education. Okay, because education can be ordinal variable. It can be above college, above high school, above secondary. Okay, so that kind of ordinal scale is also possible. So better you specify. It is a ratio scale variable. It measures the number of years. Okay, which is preferred than ordinal. Okay, so you give this kind of thing. And then for intercept, you just write constant. You can also write intercept, that is also fine. But constant is more common. Okay, and you put the constant at the bottom of the variable section. You present the variables first, x variables first. Okay. So yeah, B1, B2, those slope coefficients, you present first, and then below that, you put the intercept, B0. In SPSS, constant comes on the top. That is not good. Okay? So when you present it in the paper or in the report, you have to change. You bring the constant or intercept at the bottom. Okay? So don't just copy SPSS. Okay. And then also, yeah, importantly, you have to present the p-value. Okay, not just coefficient, but together with coefficient, you present the p-value. Yeah, you could also present other statistics produced together, like p-value, or t-statistic, or standard error. But if you have p-value, usually it's sufficient. It suffices to show the p-value because t-statistic, standard errors, these are all indicators of statistical significance. Okay, p-value as well. So it's kind of redundant if you show everything. Okay, so you show the variable name, coefficient. Okay, definitely you have to show coefficient. And then one more thing is indicator of statistical significance. So p-value, t-statistic, standard error. Okay. Yeah, whichever one is fine. But for this class, let's stick to p-value for practice purposes. Okay. Okay, and then of course, not only independent variables, but you have to specify the information on dependent variable. Okay, so usually in the margin, okay, like here below, or sometimes at the top, as part of the caption of the table, the title of the table, you can include the dependent variable. But if not, you have to specify it somewhere. Okay, so this is one method. Dependent variable, non-agricultural income, Philippine pesos. Okay, you put the unit. Otherwise, it will be difficult to understand the coefficient. Okay, and then you have to show the sample size. Okay, you know the sample size. You know your own sample size. Okay, because you are the master of your data set. Okay, then F statistic, p-value. So these things are for the overall model, not for the specific variable. Yeah, so it is customary to show this kind of overall statistics when you run some estimation. Okay, so this is also common. Okay, so F statistic and p-value, these are set. If F statistic is big, then p-value will be smaller. Okay, so overall model is also significant because this p-value is small. Okay, now one last thing, R squared. What is R squared? This is basically square of correlation coefficient. If there's only one variable, okay? If it's a simple regression, if it's a one independent variable model, then R squared is the same as square of coefficient of correlation. Okay, so remember, coefficient of correlation, it takes the values between +1 and -1, right? So that means when you take the square, what will be the range? The possible range is between 0 and 1. Okay? Okay, between 0 and 1. Okay, so basically, The larger number means the model fits well. Fits well means the independent variable explains the dependent variable to a good extent. Okay. So basically, the larger R squared, the better. But that is not the most important thing. The most important thing is the coefficient, each coefficient, this one, and the p-value. Okay, that is your purpose. Okay, but it's customary to show this kind of overall statistics somewhere in the table. Okay, as good practice. Okay, then let's take a break for 10 minutes. N number you don't find in the regression result. So you have to so you have to look at the summary table, summary statistics. Yeah, it's not very convenient. Yeah.
What is it?
Okay. Oh, now it works. Okay. So you just executed these lines in R. Okay. So I already explained this one. Oh. Yeah, this one. Okay. And then you organized the result this way. Okay. So what is the implication from this result? Let's just put it qualitatively for now. What is the implication of this table? What was your interest?
The effect of schooling on income.
Yeah, that's right. Okay, so you wanted to see the impact of schooling on off-farm income. Okay, and then Does the result support it or not?
Yes, it supports.
Yeah, it supports because you found you found the positive and significant coefficient. Okay. Okay. So significant means this coefficient is not 0. So the next thing is this coefficient is not negative, it's positive. Okay. So two important results: significant and then also positive. And that supports your hypothesis, right? Because you expected that the education, at least to some extent, influences the income. Okay, now quantitative interpretation, we'll do it later. Okay, when you introduce a multiple regression with more than one x variables. Because with one x variable, it doesn't make much sense because it's just like correlation. Okay. Okay, now in terms of presentation, we often use asterisks to indicate the statistical significance. Asterisk. This one. Okay, star. Sometimes we call it star. But more formally, asterisk. Okay, so when the statistical significance level is high, that means when the p-value is small, then you put many asterisks. Common practice is maximum 3. Okay, so according to the significance, according to the p-value, you put either 3 asterisks or 2 asterisks or 1 or 0. Okay, so if the coefficient is not statistically significant, then you don't put the asterisk. Okay, so this will help the readers to get a quick idea of which variables are significant. Because in the actual analysis, you include many variables. Okay. So it just gives some assistance to readers, facilitate the reading. Okay. But the specific methods, okay, so where to put the asterisks and how many asterisks, it depends. It depends on your definition. It depends on your method. So some different examples. Okay, example 1. So this one, yeah, first of all, put in the asterisk on p-value. Okay, which is not always the case. Sometimes you put the asterisk on coefficient. Okay. So example 1, asterisk is on p-values, and also in terms of the number of stars. Typically, in social science, we use this one. When p-value is below 1%, you use 3 stars. If not, if still below 5%, you put 2 stars. If not, if the p-value is still below 10%, then you show 1 star. Other than that, you don't put a star. So when the p-value is larger than 10%, you will not put the asterisk. That is one common way, common method. Okay, but sometimes you make it more strict. Okay, so you don't allow p-value between 5% and 10%. You don't consider them, you don't show them as significant. Okay, so in that case, the triple star goes to p-values below 0.1, for example. It depends on your definition. Okay, it's not a rule, just an example. You can decide. Okay. Okay, and then a double star goes to when p-value is, okay, so when p-value is below 1%. Okay, so instead of this one giving 3 stars, here you give only 2 because you are making it strict. Okay, and then when p-value is between 1% and 5%, you give 1 star. Okay, so that is an alternative method. Okay, so that is the difference between example 1 and example 2. Now, example 3. Example 3 is a method in which you put the asterisks on the coefficients, not the p-values. This is also convenient because then the readers who don't have much time, okay, they can just look at the coefficient. Then capture the information on coefficient and also significance at the same time. So they don't have to look at the 2 columns. So this is also a good method. Okay. So you don't even have to look at p-value. Okay. So by only looking at the coefficient, you can tell positive, negative, significant or not. So all the necessary information is there. Okay, but you still need to show p-values. P-value or some kind of quantitative indicator. If not p-value, then standard error or t-statistic. Okay, you cannot omit. Just putting asterisk is not good. It's not professional when you are presenting a statistical table. Okay, because you have to allow readers to interpret it their own way. Okay, so asterisk is your threshold. Okay, it's your standard, but readers may interpret it differently. You may not allow p-value 0.08, but readers may believe in the result with p-value being 0.08. Okay, so you have to allow readers to make their own interpretation. So that is why, although you put asterisk, it is common to put asterisks, you also have to show the actual number. Okay. Okay, so basically you decide based on what you want to emphasize. Okay. If you want to emphasize very small p-values, then the more stricter method. Okay. And if you want to emphasize not just p-values but also the effect size coefficient, then maybe this will be more appropriate. Okay. So it's just a matter of presentations. Okay, so now we estimated the simple regression, right? And then found the coefficients. So one thing you can do, which is not very important, but one thing you can do is to insert the actual estimated numbers into the equation. Okay. replacing the notation like B0, B1. You can consider the actual number. Okay? So this is the intercept. This is the slope. Okay, the slope is applied to x. And this whole thing up to here is y hat. Estimated y. That is the line. Okay, not the actual. Actual is this one. Actual includes the error term. Okay. So y hat is the predicted y, predicted value of dependent variable. Okay. So in the data set, it will look like this after the analysis. So this is what you have from the beginning. Okay, respondent ID, and also the actual income that you collected. So before the analysis, you already have it. This one, education as well. Okay, so after the analysis, you get this predicted y and epsilon. So this depends on the model. This depends on the analysis. Okay, so sometimes you can consider the predicted value of dependent variable according to whatever the value of x. Okay. Yeah, because you can do prediction based on any number of years of schooling, not just these actual existing values. Because you establish the slope, okay, and the intercept. Then, for example, if you want to know education 7 years, okay, so not here, but what if education was 7 years, years of schooling was 7 years, okay, and what would the non-agricultural income be based on the coefficients? So that is something you can calculate. You just insert X number here. Okay? Yeah, so let's look at the epsilon residual. It takes both positive and negative numbers. Okay? So this gives you some understanding of this epsilon being random. Okay, it's random around 0. So ideally, when you take all the sum, total of all these values, okay, for epsilon, it's supposed to go to 0. Okay, that is the ideal situation. So this error term, you want this term to be as random as possible. If it's random, then it will be sometimes positive, sometimes negative. But when you take the total, then it's supposed to be almost 0. Okay. Okay, now you plot these. So actual values, actual dots, and then estimated line. If you plot it, it will look like this. Okay. So years of schooling is discrete, only integers. So that's why it will look like this. Okay. Then the estimated regression line. This line actually looks this way. So here's the intercept, B0. Okay, and B1 is the slope of this line, which is positive, not 0. So this shows there's some relation, positive relation, between years of schooling and off-farm income. Okay. Yeah. So can you associate this graph with these values, these indicators? Y hat. Where is y hat in this graph? It's a line. It's this line, okay, dotted line. Okay, so these values are y hat. Okay. Yeah, I already explained yesterday. So this is an indicator of observations. So in this case, household. Okay. This one without hat. This is the actual line, actual income. Okay. So these red dots, all these dots are representation of y. How about x? xi. Xi is the values on the horizontal axis. Okay, so it can be 0, 1, 2, 3, 4, 5. Only integer values. What about epsilon? Yeah. So epsilon is, for example, for this dot. Okay. For this dot, epsilon is the distance between the dot and the line. Vertical distance. Okay. So you don't measure the distance shortest. Okay. It's not this right angle. It's not this. It's the vertical. Okay. Vertical distance. This one. This one is the error. Okay. So it can be negative. Okay. Any questions so far? Is this equation a good model? Yeah. So equation means this line, okay? So this line, is it a good model to represent the relation between these two variables? Yeah, it doesn't look so good, but there is a significant relation, okay? But this x alone, this education variable alone doesn't explain much, okay? Although there is a statistically significant relationship, okay? So that means you have to consider many other things as well. Oh, what happened? How do I? Oh. Okay. Yeah, the last one. Now, we talked about prediction, right? Prediction means based on the result, based on the coefficients. Okay? Then one thing you can do is specify x variable, okay, the value of x, and then estimate the y that corresponds to the specified x variable, x value. So that is a so-called prediction. But prediction can be used only in the data range. Okay? What does it mean? So actual data exists between, in terms of x variable, okay, between 0 and 14. So it doesn't have a value above 14, or it doesn't have value, negative value. Okay. So the actual data range is here from 0 to 14. So prediction, if you want to use, can be used only within the actual data range. Okay, so you cannot use it for like 30 years, 40 years of schooling. Maybe you want to estimate. Okay, what if someone has 30 years of schooling? Then what would be the estimated, predicted level of farm income? Maybe you will think about that. Okay, but it's not appropriate because the data do not exist in such range. Okay, x being 30, 40. So outside the actual data range, you're not supposed to do prediction because it's not precise. Okay, because this relation is based on this specific range. So you should not go too far beyond. Maybe for 18, 19, this kind of number, okay, but not 30, 35. Okay? So that is one thing you have to note if you want to do prediction. Okay. Yeah, and of course, when you want to do prediction, then the coefficients have to be significant, first of all. Okay? So if the slope coefficient is not significant, then you cannot do prediction. Okay? Because that means there's no relationship between x and y. There's no way you can predict y from x. Okay? So that is the basic requirement. The result has to be significant, small p-values. And you do the prediction within the actual data range. Okay? So if these two do not satisfy, for example, if the coefficients are not significant, or if you want to think about some x values beyond the range, far beyond the range, then the best prediction of the value of y is just y bar. Y bar is the sample average. Okay, so just use the sample average. You don't calculate this y hat. Okay, if the coefficients are not significant, or if the data range is, if the value of x you consider is far beyond the actual range. Because the estimated coefficients b0, b1 are not relevant. Okay, so if not relevant, you cannot calculate that model, that equation. So you just use y bar. Okay, if you want to predict. Okay, so reminder, prediction is not the main purpose. Okay, finding the coefficient b, slope coefficient, that is the most important purpose. Okay, and also simple regression, that means one independent variable regression, is useless because of what I explained yesterday. Because other factors are not controlled for. Okay. Okay, then please go to the next slide. Okay. Stop share. Yeah, class 11, 12. Let's open this. Okay, so earlier we discussed a qualitative interpretation of the coefficient. Okay, significant or not, and also positive or negative. But yeah, if you have the regression results, then you have to provide some quantitative interpretation as well. Okay, so otherwise you are not really harnessing this analysis. Okay, you're not taking enough advantage of this. Okay, so here we introduce one concept, marginal effect. So basically, the coefficient, slope coefficient, captures effects, effects of x on y. Okay, but in a linear model, that coefficient.
Oh, Professor,
Yes.
I think the screen is shared. Yeah.
Okay, okay, not shared, right?
Thank you.
Okay, now in a linear model, formally, the estimated coefficient represents the marginal effect, marginal effect of x on y. What is marginal effect? Marginal effect is the change in y as a result of a change in x by exactly 1 unit. You increase x by 1 unit. Then see what happens to y. Okay? So the change in y as a result could be negative. Okay? It could be positive, it could be negative, or it could be insignificant, 0. Okay? But the point is, when you consider marginal effect, you are increasing the independent variable x by 1 unit. That is the definition. Okay? Okay, so the marginal effect is the marginal change in y that occurs when x changes by 1 unit, when x increases by 1 unit. Okay? And that is what's captured by the coefficient. So that is the meaning of the slope. Example. Earlier we found this one. Okay? And then slope coefficient was 2,906. Okay? So this slope tells you if we increase education by 1 year, then the predicted value of non-agricultural income will increase by 2,906 pesos. Okay? Yeah, another way to put it. For every additional 1 year increase in years of education, we expect the non-agricultural income to increase by 2,906 pesos on average. So on average means it's not for each and every household, but as a group, okay? For the full sum, for the full sample, on average, this will be the effect. This will be the increase. For some household, maybe it increases by 3,200. Some households, maybe it increases by 2,700. Okay, but on average, it will be increase will be this much. As you increase the x variable, by one unit. So in this case, one unit is 1 year, because x is defined as years. Okay. So it can be other units for other variables. Okay, it can be number of people in the family. Okay, and sometimes it can be gender. We will discuss it maybe next week. So it can be many things. X can be various things. It doesn't have to be number. So all kinds of things we can analyze. The effect of X on Y. Okay. Any questions so far? So when you get the results, you're supposed to provide this kind of interpretation, quantitative interpretation, for the significant coefficients. Okay. If it's not significant, if the p-value is large, you cannot say this. Okay. You just say the result is the coefficient is not significant. And then you will not provide this kind of quantitative description because it's not appropriate. Okay. Okay, any question so far? Online students, are you with me?
Yeah.
Then you're okay?
Yes. Okay.
Okay. Okay, so if fine, then next Wednesday, then we will start discussing multiple regression. Okay, so see you at 4 p.m. Wednesday next week. So if you missed some part of the class, then please watch the recording. Okay.
Thank you, sir.
Okay. See you next week.
Thank you, Professor. Thank you, Professor.